Hi, everyone. This is Plasma Call number 8, lucky number 8. And in this call, we're doing updates, talking about splits and merges, and various other fun topics. Shall we go around and talk about perhaps updates, things we were thinking about, things we were designing, things like that?
Yeah.
Anyone can start.
Okay.
Todd.
Shall we go around like in order? So Aditya and then head down. If there's no updates, just say no updates.
Perfect.
Yeah, so we're the Blockchain Berkeley implementation team. So we're working currently on implementing Plasma MVP with 5 devs from Blockchain Berkeley. But we've been thinking about Plasma Cash as a possible next step after that.
Cool. Are you guys all in Berkeley right now?
Yes, we are.
Cool. Do you guys want to introduce yourselves in more detail?
Yeah, so I'm Aditya. I'm a sophomore working on this semester. So I've been building a lot of the root chain and side chain stuff.
Yeah, I'm Colin, and I've been doing pretty similar stuff. And I just joined Blockchain at Berkeley this year.
Cool.
Yeah, so we have an open source repo, so we'd love to have more eyes on it. So
post the link in chat so we can post it on the YouTube.
For sure.
Cool. And then what do you want to give a quick description for people that might be interested to convince people to click the link, like languages and things like that?
Yeah, so we're implementing the sidechain with the Cosmos SDK. So just getting the networking and consensus done with the SDK, and we're just building on top of it to do the application layer stuff. And so I think that's pretty interesting. I'm not sure if there's anyone else doing that. But then we also have a lot of research documents based on our implementation and about just Plasma in general that we think would be really interesting. For example, we had published on ETH Research an attack vector that we had found that we think is pretty useful for other implementations to be aware about. And then we also have things just ways to optimize the throughput on Plasma that is on our repo.
Cool.
What's the post on ETH Research?
It is called, I think it's called Civil Transactions.
Okay, I must have missed that.
Cool. Lee and then Bun, maybe. Updates, any thoughts? If not, can pass.
No updates. I'll pass.
Cool. And then Bun. Sue.
Taiwan.
Oh, you're muted. Maybe that's why.
Yeah, they are muted.
Sorry, I'm started their fourth fortune GitHub repo, so I didn't wait. So we are currently working on Plasma Cache under Omisego repository, but I think we are still in the pretty early stage.
Very cool. And yeah, a lot of fun exploration and research to be done. And Dan, I hear you were talking to Carl or something like that when it comes to thinking on things and research and fun stuff when it comes to leading a lot of the thinking on Plasma Cache.
Yeah. So we met up to chat about Plasma Cache stuff, and I think we concluded that with merging and splitting, you can do it with the challenge being having size proportional to the number of merges or the number of so for splitting is a little harder to exactly price out, but for merges you can do it as long as the challenge, not necessarily the attempt if it's unchallenged, but the challenge has proportional size to the number of merges in the coin's history. So not terribly bad necessarily. So at least something I think worth with sort of trying to spec out. But yeah.
What do you mean by proportional?
I mean linear time.
Okay.
So the number of when someone attempts to withdraw and merge coin, the attempt is proportional just to the number of coins that they're trying to withdraw. It's linear and just coins, which is fine, and sort of necessary. But then the challenge has to reveal all the coins, all the merges in that coin's history. In the challenge, in the coin that you reveal as a challenge, is reveal all the coins in your history. So it ends up having size. That challenge is having size linear in the number of merges in that coin's history. So
is this still the same merge protocol in your old research post?
I think so. Yeah. There I might have suggested. Yeah, I think you made the point. I hadn't realized that you do end up needing to reveal all the merges. So that one of the parties has to reveal all the merges in their history. So the other party merge the challenge.
So with that caveat, this is the.
Yeah, I think so. Yep.
So. Okay. I might ask more questions later, and then after everyone runs through, I think. To map it out for everyone, I guess.
Okay.
And then Poma, Andy, and David, in that order.
Hello, I'm Roman from Bankex. Usually you have Alexander here, but today he can't come. We are in the final stages of testing our Plasma MVP. We are currently writing tests for Plasma stopping when someone finds invalid transactions and prove it to the smart contract. We expect to release it about early May.
Cool.
And then Andy and Lynn.
I'm just a part of Taiwan Plasma team as well.
Okay. And then Adrian and then David, I guess.
So we're starting to work with Adida on helping the Berkeley team build their Plasma installation on top of the SDK. So that's where we're at right now.
Mm-hmm. And what's the general idea with the blockchain at Berkeley? Like, are you guys mainly like trying to expand for development, and like sort of like what are you guys thinking about in terms of general blockchain development processes and things like that? It's a very tricky question.
Is that a question like for the club or for our team specifically?
Both, I guess.
Okay, so for our team specifically, we're just interested in scalability research. So Plasma was something that interested us early on. And so from there, we see like moving on from that to just working on other scalability aspects, other scalability projects for blockchains in general. But for the team, for the club, we're doing a bunch of research in different areas. So there are people working on aggregate signatures, people working on crypto economics, which Carl's
cool.
Those guys.
Is it true that your university club, you have to take a test to even join?
Well, yeah. You have to get certified, and there's like a month-long application.
The application's rough, yeah. But once you get it, it's fine.
Okay. That's
really funny.
Nice me when I heard that. Yeah.
I know they do. I heard they do security audits as well.
Yeah, there are people doing that.
Yeah. Oh dang. Okay, David, how are you doing?
I'm good. I've been thinking some about kind of like the potential to add atomic swaps within the context of Plasma MVP, like atomic swaps between a Plasma chain and then Ethereum, and then trying to think about state channels within the context of Plasma MVP and liking Plasma Cash even more, because particularly with like basically state channel, like lightning style state channel stuff, where you basically have a bunch of transactions that you're making that reference each other, but that if everything is going correctly, you're not actually submitting it to the blockchain. They're just there for security purposes. Basically with Plasma MVP, with confirmations, or with the current like no conf plasma MVP style setup, that kind of back and forth theoretical transactions, I at least so far haven't been able to find like a way to make it work. But I have good feelings about like, I've thought about it a bit within the context of Plasma Cache, and just because it doesn't have those limitations, I think it'll be a lot easier to implement.
You're just implementing HTLCs.
Yeah, exactly. Pretty much. Yeah. And then thinking about like exit delegation, particularly for Plasma MVP, or exit initialization delegation, and exit bonds, and then potentially for Plasma Cache, some sort of like checkpointing. Yeah, but at least so far, that doesn't seem promising, particularly when I've thought about like operator checkpointing within the context of also supporting merging and splitting. Yeah.
Cool. Janti, do you have any updates? If not, we can pass and move on.
No.
Okay, cool. And then I guess the one question I had from the updates is I guess more detail on like the merging question. I guess Dan is with merging. Basically, the presumption is under the situation is you have to be publishing the splits and the merges upon exit. Is that what you mean?
So I think you have to publish the splits. I think you only have to publish the merge transactions that are like in the transaction history of that coin if you're challenged.
Yeah, I think that makes sense for sure. Yeah, I think that definitely makes sense, because basically the split basically specifies which TXO, and you need to identify it. So I feel like you have to identify it that way.
Right. And for the merges, similarly, you have to specify all the coins you're withdrawing. Otherwise, tokens you're getting.
Yeah.
So it's doing that.
Is it possible? I guess this is a minor like implementation, optimization, or detail. Would be that I guess every piece along the tree, I presume it's assumed that every piece along the tree has a unique identifier, so that if it's like let's say it's what is it, a 7-level a tree with 7 elements, including the branches, which is a parent child assuming a binary tree, then I'm presuming that there's 7 IDs within each, and then at that point you can just identify a single withdrawal if it was a single one, I presume.
You're saying if you're claiming a split?
Yeah, or claiming a merged coin, a split and then a merged coin from that split or something.
Well, right. So I think you have to specify. So you have to like specify to the parent chain the splits, right, in order to like tell it what splits have happened, so that people who have like cousins of that split coin can challenge it. And then when you usually have to do that anyway. And then when you do the if you do a merge of like 2 split coins, then each of those splitted coins have their own ID. So you just specify I'm going to get this coin, which is a splitted one, and this other one, which is split off of some other one. What you have to declare is just so it's just 2 IDs, I think.
Okay. Well, it could be a lot depending upon if we're structuring it as not a binary tree, which might be the case. I guess I don't know. I guess
but I don't think it's that bad. So like when you split coins, if you imagine like you've just specified here's the amount that you're splitting into this branch, and here's the amount you're splitting into this branch. Then you can just and you say like this is just branch 0 with amount 3, and this is branch 1 with amount 2 or whatever. Then you can just hash that, and now you have a 32-byte ID that uniquely identifies that coin. So you have to declare that to the parent chain. You say I'm splitting the coin at this location.
Right.
But then, like once you've done that, and now like it's sort of as if those are 2 separate deposited coins. you can just treat them like then you just say like, now I'm merging coin with this 32 byte ID and this 32 byte ID. It doesn't matter that they've been split before.
Wait, your description is there's no restriction that you can only merge sibling coins?
That's right.
Oh, that's different from, okay.
Yeah, so the idea is that you create some brand new coin by like hashing together the IDs of one coin and the other coin.
Right, okay.
And you have to declare this merge on both of the coins.
Yeah, the places.
In each of those sort of slots in the tree. But once you've done that, now it lives in a completely different slot together, like marriage. I use a lot for this. So like, there's going to be cousins getting married and stuff. I don't know. Probably this will break down, but
only cousins are allowed to get married.
That's right.
If I'm understanding you correctly, the tree you're talking about when you do a merge, it doesn't get deeper. It just creates a completely new ID based off.
It gets wider.
Got it.
Yep. And I'm assuming here we're using a sparse Merkle tree rather than like I think some designs have been just like a very small Merkle tree where every ID is just an incrementing integer. And so this one assumes you use a sparse Merkle tree where every 32 byte ID is an independent slot in the tree.
Oh, okay.
So yeah, I mean, is everyone familiar with how sparse Merkle trees work? Like it basically looks like you have a Merkle tree of 2 to the 32, 2 to the of a lot of elements, 2 to the 32 elements.
Wouldn't it
2 to the 6 elements? Anyway, yeah, what's that?
Wouldn't it increase the size of proof when you?
Not much. It might increase this. Yeah, it might increase the size of the proofs a little bit, but like your tree is still tracking. Most of the tree is considered empty, so you can like pre-compute what it looks like when you have a whole section of your tree that is empty, or like. Sorry.
Yeah. So basically, when you transfer one coin more than like 10 or 20 times, your proof size will be a lot, right? Because you have to provide a proof like.
You're talking about just because of the depth of the tree?
Yeah.
Yeah. I mean, the depth of the tree is just like it's just sort of logging the number of elements in the tree. So it doesn't end up being that big. And I think, if you've got like some reasonable number of outputs, you're going to have like some large number of outputs in this tree anyway. So I don't think maybe it'll double the size.
Well, without any compression, it'll be 32 elements long from the one you described.
If it's too,
you can compress some of them.
Yes, right. And I mean, a proof, yes, a specific proof would be 32 elements long, I think. I'd have to. I'd refresh myself on that, but yeah. So I think that certainly makes it easier to do things where you're merging coins together. I don't know. Yeah, I mean, I don't know. Maybe you could probably do it if you just have. So, are people right now when people are thinking like, here's the design for it? What kind of data structure are you thinking of?
So Vitalik proposed like Patricia tree also can be used here. So.
Yeah.
So this was before the magical moment where Vitalik realized that sparse Merkle trees ridiculously destroy Patricia Merkle trees. Patricia Merkle trees are dead tech, declared today. Sparse Merkle trees, you get the same efficiency, if not better, and insanely simple, comparatively speaking. It is, and Vitalik actually has. I can link to you a like sparse Merkle tree like proof checker and addition. It does all the operations that you'd like. And so let me actually link that now. But sparse Merkle trees are a godsend, and we are going to be using that for Ethereum mainnet and for Plasma and for everything.
Is there? I guess you don't even need like a native. Like operation for that in terms of the EVM, right? Because it's just like hashing, right?
I've asked Vitalik this multiple times, and yes, he said that you don't even need it, that it should be efficient enough. So I just trust Vitalik.
Yeah, I'm presuming the gas cost is probably like irrelevant under that context.
Yeah.
Yeah, if you can post it into chat, I think for people that haven't seen it yet.
Yeah.
And then you can do. Can you do proofs of exclusion on? I feel like I've already asked this before.
Yeah. I mean, proof of exclusion is identical on a sparse Merkle tree to a proof of inclusion. In fact, it's actually can be shorter.
Oh, really?
Because because literally you just say like this. Well, I don't know if it's shorter. I think so. Because like literally, just, like it's pretty simple. If like half of your sparse Merkle tree is empty, you just need to show like one element. And you say that's the empty element that shows that all ones are empty.
Yeah.
You know, it won't usually be half, but it'll be like some huge chunk will be empty, and you only have to walk down to that point in the tree. I think that's similar to the. I'm honestly, I'm rusty on Patricia Merkle trees, but I think that's somewhat similar to how Merkle trees work on it. But it's very simple to conceptualize with sparse Merkle trees. Yeah.
For the viewers that are less experienced with Ethereum, this is Patricia trees are used in Ethereum currently for basically everything, including account management, and is computationally one of the, if you, I think, I could be wrong, I think if you did a profile on where a lot of the computation is occurring, I think a lot of the computation and IO is for this specifically. This is like where a lot of the work for the blockchain, the P2P node, the full node is actually doing a lot of the work.
Can I just check if this is the paper that's the same sparse Merkle tree? I'm not familiar with it.
Yeah, I mean that's at least what I'm familiar with sparse Merkle trees from is this paper.
Okay.
This is the basic idea, yes.
Just to comment on Patricia Merkle trees, it's how Ethereum works. Don't learn it. Don't even look it up. Don't even do it. It's bad for you. No one knows how this thing works.
It's complicated.
It's bad.
Well, it's good. It's good for what it's done.
Yeah, it's done amazing things.
Yeah.
It's just like when you have this alternative, just use the alternative.
And I think it should help on space significantly in many situations as well. Is the improvement?
Yeah, especially since the vast majority of your proofs are non-inclusion proofs in a given off-chain proof. You're mostly proving non-inclusion. So.
Oh yeah. I mean, obviously, yeah. I mean, I asked about non-inclusion for that reason, but I guess that definitely makes it very, very real.
Yeah.
Oh, that's cool. Yeah.
If you're doing on-chain, and that's basically what you're computing. What's interesting is that, like, I think this topic, I think, is very relevant for people that aren't even working on Plasma, because like this problem of needing to make Merkleized commitments and proofs is a very, very, very common problem for a lot of smart contracts, because if you want to be able to make compact proofs on a lot of data, then basically this is basically the avenue that you're going to go down, barring really elaborate fancy cryptography, which is good too, but oftentimes making compact proofs you may want to keep it to straight Merkle trees, and this is very important to know whether something is in something, and then basically building some kind of index off of it. But yeah, is someone writing like Solidity code to do this? I think it's like a fun, small, tiny project for someone, right?
Viper code to do it, right? Solidity's awesome. We're not going to write the technology of the future and the language of the past.
David, what do you think about that?
I am a huge fan of Viper. I'm definitely pro.
You need to get full disclosure on that one, man.
Don't deploy Viper in production yet. But,
I don't think you should deploy Solidity in production either. So.
Oh snap! You went there.
That sounds right.
Oh man. Oh yeah.
Nice.
Anyway.
But no, I think with Viper, do you want to give a quick mini commentary on Viper, David? Since this is your wheelhouse, and I think a lot of
Sure. Viper is a safety-first smart contract programming language. It's totally different from Serpent, which was kind of an ancestor Pythonic smart contract programming language. The compiler for Viper is written in Python as opposed to C++, so it's significantly smaller and kind of to understand and maintain, just to kind of check over and make sure everything's working the way it's supposed to. And the design goals around Viper are basically to try to make it as safe and secure as possible by giving developers the functionality they need, but not functionality that can be super dangerous, like basically running with scissor style stuff.
Cool.
Yeah, it's kind of short.
So yes, I mean, so it would be a pretty good like language for writing stuff like this, right? These sort of protocols for just Merkle trees, Merkle tree verification, right?
Yeah, definitely. Super clean, easy to understand. If you, for the most part, like it is different than Python, but if you're coming from Python, it's not too big a jump.
Yeah, I think if there's example code in, I believe, Golang, I think it could be a fun research project for students or something like that, or someone learning about this space and learning programming in this space to write it in, whether it be Solidity or Viper, and sort of explore that in terms of processing the proofs.
Yeah.
And verification of inclusion and exclusion.
And even more generally, I think basically putting cool cryptographic stuff, actually writing that in smart contracts is super valuable, because there are so many cool papers out there that exist, and occasionally you see like code in C++, but they have a lot of practical use cases, particularly on the verification side in smart contracts, and it's very hard to find examples to work off of. And so, yeah, push the ball forward.
Yeah, and as for a lot of the people new to this space, and I think it includes a couple people in this call, but I think it's more for the viewers, the sort of conceptual design for a lot of Plasma's construction, but one should take in general when it comes to smart contracts, is a focus on processing proofs. You're doing the computation on your computer, and then what you're publishing to the blockchain is essentially a statement of computation, and generally it's viewed as a commitment, where basically you are saying, hey, this is the result of what I'm doing, and you're being supplied sufficient data to be proven whether it's correct or incorrect of what you're attesting. And what that gets you is that essentially all the computers that everyone's computing in the world, because if everyone is computing the blockchain all at once, it's not necessary to actually do the full computation. It's that you just need to show the results and ensure that it's provable or disprovable. This should be pretty basic for a lot of us on this call, but I think this is it's a pretty important thing to understand. So an example of this in relation to this tree structure, this Merkle tree structure, is that you're not creating the Merkle tree on the blockchain. You're verifying that the information is correct or incorrect primarily. Yeah. Sorry if this is like a little bit belaboring the point for everyone on this call.
No, I don't think it's basic.
No, this is a good point.
Actually,
they need to new people.
Yeah, and also I think like this is something that would be really cool to develop a language for, and I don't think anyone has, is I know Peter Todd is working on something like this, is a language where you can specify like a proof in terms of like, here's what I want to prove with these Merkle trees and this inclusion and these sets and whatever, and it generates a prover and a verifier for you. So instead of you having to sort of write and figure out and like try to test your intuitions on like, okay, this proof, this should work and it should be pretty efficient, if you could instead just specify, here's what I want to be proven, and have something generated.
Yeah, I think on the Ethereum side, I think the TrueBit project is an example of that, where they're basically trying to create a generalized compiler, and then specifying the Merkle proof of exactly whenever the data is incorrect, and basically playing an interactive game in order to essentially play out exactly where the incorrect computation has occurred. I don't know if I don't think there's like an example full implementation, but I think there's exploration along those lines.
I think they do have like an OCaml compiler that compiles
cool
code to like into a prover and a verifier for it. So it's pretty neat. But yeah, so that's true for TrueBit. And then yeah, I think it would be cool to have that for sort of plasma type protocols as well, where you just say like, well, what I'd really like is some way to prove non-existence of it in this space. And then you say, here's a proof that you could do like a long proof, and here's an interactive economic proof, and here's a ZK snark, and here's
I see what you mean. Yeah,
there's a lot of alternative. Here's just sort of like proof by assumption. It'd be like an honest majority minor assumption or something.
Yeah. Or
you can trust different things. So I don't know.
Yeah. Or using elaborate crypto like
there's
like accumulation or something like that.
Yeah.
That's a good point.
Yeah, I don't think this is sort of basic at all. In fact, I think it's very counterintuitive when we're used to writing code, like we're used to designing stuff, like we do it in heads or whatever, and then we just write code that proves and verifies it, and we try to figure that out with intuition. Is that to really think about the primary thing that you're doing is not running. You're verifying and generating proofs.
Yeah. I think this is a topic that it's funny because when I'm talking to you, Dan, or Carl, or David, or anyone else on this call, and like Adrian, I think I've talked to you about these topics a couple months ago too, where it's like this is all presumed, like this is all presumed knowledge, with the set of people we're talking to, and it's just I think there's very little documentation. There's a lot of conversations that you can find online, which says like, oh, by the way, this is important. But I think a lot of people new entering into the space don't run on that assumption.
Totally. And if people are entering the space and don't know a lot about crypto economics yet, there is now / soon a resource that they can go to, which is cryptoeconomics.study, Carl's course online for the Blockchain Education Network. Carl, do you want to plug that?
Oh my God, Dad, you just teed that thing up.
Is there a section on this in your class?
Oh, of course. I mean, accumulators. I'm going to be talking about Merkle proofs. I'm going to be talking about all.
But the importance of proofs.
Oh, I mean, absolutely. And if there wasn't before, there is now. This is super, super critical. And I would say that the most important thing for me to say is, number one, I mean, there's just like a little intro video that I released like last week or 2 weeks ago. But two, there's also a form. And so if you want to make sure that things are your favorite topic is going to be included, well, then please post on the forum and let's make this course awesome. And I'm actually about to post a kind of outline of every chapter, every kind of section. And so that will go into details, just like a kind of like written outline of like what I plan. And that will be on GitHub, and I'm going to post about it, and we can, please submit pull requests and like fix up little sections of it. And hopefully this can be a kind of like open source collaborative effort for, establishing a groundwork for crypto economics as a field. So let's do it. Let's learn. Let's be awesome, y'all. And let's make the world decentralized and not forget that crypto economics actually does something useful. And it's not just, DPoS and call it a day. Anyway, that's my plug.
Nice.
Oh man. So I think the conversations we've had on Merkle trees is very, very interesting. Should we continue that, or are there other topics for people to discuss?
Yeah, just one more thing I wanted to share on that was, I think I mentioned a call a couple weeks ago that Peter Todd's been working on. I think he's working on something very general in this space with like the ability to sort of specify arbitrary proofs and compile it to proofs and provers and verifiers. But that's all. I don't know when that's sort of coming out. But I asked him by email about some of this stuff, and he sent an email to Bitcoin Dev in response. I don't honestly really understand that well. It's a little beyond me and what he's describing here on Merkle, on these special kinds of Merkle trees and proofs of publication and non-publication. But let me I'll just share that in the chat. Yeah, so he's been thinking about this sort of client-side validation stuff for a while. So, and I think yeah, it's a pretty interesting. This is sort of pretty deep on this. But yeah, Merkle mountain ranges. I don't know if people are familiar with those. There's sort of like the kind of like Merkle, relatively efficient Merkle trees for append-only logs.
That construction is primarily around append-only, right? Like that's optimizing append-only. It's not optimizing for space, I believe.
Right.
Correct?
So, yeah. So that's right. So exactly. So I don't. It's not a particularly good sort of like dynamic data structure, but yeah. But I think we're right. It's yeah. There's a few. I don't know. There's a few sort of ideas in here, but generally, yeah. I think the more people get familiar with and that sparse Merkle tree paper is really good too. Yeah, I think these data structures just getting sort of familiarity with these. Oh yeah, also Bloom filters.
Oh, this is a fun topic.
That I need to add.
Like the sort of rule of thumb is usually like it's never a Bloom filter. Like don't use a Bloom. Like if you think you should use a Bloom filter, you're wrong. But maybe here you should use a Bloom filter.
I think yeah, I'm pumped about Bloom filters as well.
Cool.
Kelvin, who is doing plasma research as well, has been kind of further exploring their viability, and particularly if people apply client-side software that basically can optionally get like a Bloom filter or just track proofs of non-inclusion depending on kind of basically the assets you need to track. Yeah.
Depending on what, sorry?
Depending on like the assets that you need to track, because if you only have one coin, you don't necessarily want to keep the whole Bloom filter. But if you're, say, a merchant interacting with a lot, then you start to see huge efficiency gains with Bloom filters.
Yeah. So the idea is that the Bloom filter is part of the protocol, or it's just sort of like it's part of the protocol, like the Bloom filter in every plasma block header. What is sort of what do they think is sort of the ideal tuning for that? Because like
all right, guys, I have to go. It was great talking to you. I'll talk to you in 2 weeks. Thank you very much.
See you, Adrian.
All right, see ya.
All right.
So like on Bloom filters, you can I mean you can actually tune down the probability of like a false positive to extremely low. Although that's not necessarily like if there's an adversarial attack on it where someone generates an ID in order to cause a collision, that can be sort of a problem. So you don't want to rely on that necessarily. But like the problem with Bloom filters, right, is that within it only scales on like the size of the number of elements, right?
Yeah.
So like how large a Bloom filter would they be thinking in the headers?
Like, well, you wouldn't, in the headers, you would have like a large Bloom filter, and then you'd commit like a root of it that people can check, right?
Right.
What set do you commit to? Like, do you use the Bloom filter to track?
Transactions in that block, right? Or coins touched.
Transactions in the block, okay.
Mm-hmm.
Or like coins touched in that particular block.
Yeah. So I worked a lot with Lalu on the Bloom filter constructions for Neutrino. Essentially, one thing that didn't get into there that may be helpful to do in this situation, if the load becomes sufficiently high, is don't forget that you can filter the Bloom filter itself before you enter into the Bloom filter. So, by what I mean by that, and that sounds like lunacy, is what you can do in terms of Bloom filters is that, for example, if you wanted a Bloom filter of addresses or outputs, for example, you can filter things into, let's say, 64 buckets, right, of addresses or outputs, let's say, and then you filter by outputs, and it only goes into a specific Bloom filter by that output. So, for example, if it starts with a 1, it goes to bucket 1. If it starts with 2, it goes to bucket 2. And then that way, on the client side, if your wallet only generates addresses starting with 1, you only need to watch that Bloom filter, and the amount of filter downloads that you do drops substantially. And what that gets you is a lot of fun because that makes it so that you just grind outputs, for example, until you get the desired filter that you want. It's just something to keep in mind with bloom filters that you can do by pushing more work on the client side.
It's like an interactive bloom filter.
Yeah. That's something to keep in mind in terms of optimizations. But I don't know where Dan was going with his bloom filter thoughts. David, what have you been thinking of with bloom filters?
Basically, kind of thinking more about the actual size in terms of what would be needed based on like Dan's proposal. And then not only tracking token touches, but in the situation that you kind of get a false positive, I was kind of thinking if there's a way, like once there is a false positive and that's found, if that could almost be re-put into the bloom filter.
False positive. What do you mean by a false positive? False positive within the filter. So it is in the filter, but not in the block. So the presumption is that you only need to do work on false positives? Sorry, I still don't follow.
Yeah. I'm pretty sure that's the presumption, because you're basically using the bloom filter to track spend, but sometimes like there's that small chance that you'll basically get a false positive when there has been no spend, and so in that case you need the proof of exclusion.
Mm-hmm. So the presumption is that you don't parse the Merkle tree unless you get hit on the bloom filter is the presumption. Cool. I think the bucket construction here can be helpful in terms of optimizing space as well.
That's so cool. So does the exit mechanism accept like bloom filter non-inclusions as a proof of like?
That's a lot of work. I think maybe not, right?
To me, at least my understanding of it was that it would be primarily useful client in terms of reducing client-side storage.
But the bloom filter must be therefore enforced.
Yeah.
On the as part of the consensus. So I guess the restriction would be, this is novel. So constructing a space-efficient bloom filter that is also fast in low gas cost, I think is the interesting research area here that I don't have the answer to.
Sorry about that.
Well, you need to make sure that the bloom filter corresponds to the actual like Merkle root of the transaction.
Yeah. So you can construct a proof that it's not within the bloom filter. But for example, there's a lot of optimal bloom filters out there. And a lot of optimal bloom filters run on the presumption that you can make computation trade-offs, right? So for example, things like Golem-coded sets is basically running a compression function on the bloom filter in order to create a compact bloom filter. And that might be too expensive to do gas-wise, would be my guess, to basically try to compress a bloom filter. So we may have to do more naive constructions or something else. Which is an interesting constraint. If you need to have Dan, if you just reconnected, what we mentioned was that if you had a bloom filter commitment in each plasma block, then it must be provable on chain in order for it to be useful. In terms of the commitment. The commitment in the contract, basically.
Not just verifying this line isn't in a bloom filter, but actually.
Well, you want to be able to have other people dispute the bloom filter.
I'm not sure actually, because I think you could say the bloom filter is law. Like a bloom filter is if the bloom filter doesn't include like your transaction, then you're like then the transaction is not.
Oh yeah.
So like.
But what if they falsely put in all zeros on the filter, for example?
Then it's an empty block. There's no valid transactions in that block. So
what happens if that's not representing things correctly? Is the question.
It doesn't matter. So
it doesn't matter. Oh, okay. That makes it a lot easier. If it doesn't matter.
I think because with the Bloom filter, like if you say first we look at the Bloom filter, and if it's not included in there, it just isn't in that block. And we need that property, I think, because unless you have some kind of challenging a Bloom filter on the main chain, you need that property because you want to be able to trust just a chain of Bloom filters.
Yeah, but I'm basically asking, what if the Bloom filter is incorrect and flip over the block?
Then anything that isn't included in the Bloom filter, even if it's valid in that block, isn't in that block.
I need to think about this more. I'll get back to you.
So the set of transactions is defined as all the transactions in this sparse Merkle tree filtered by this Bloom filter.
Right. Exactly. So if the Bloom filter doesn't include it, then like end of discussion.
So we do need to check the Bloom filter during exit.
Yeah.
We do? Yes.
Well, if you're using it as law, then you do.
Yeah, but you just have to check, you have to verify that one, that those coins are.
Oh.
You don't have to check. You don't have to check the.
Right. So don't check that.
Yeah.
But then you'd still want to have like the option to submit a proof of non-exclusion, right?
Well, in
the situation of a false positive.
So in order for what Dan is saying, in order for a transaction to be treated as legitimate, as part of an exit, is that it must be valid on the Bloom filter first, and then be valid on the Merkle tree in the transaction is the ordering.
Yeah.
And if it's not valid on the Bloom filter, then the transaction never occurred in the first place.
Right. Actually, I think it would work to just say like it needs to be both in the Bloom filter and in the Merkle tree.
Yeah.
Okay.
So that Bloom filter means that proof of non-inclusion in the block. There doesn't need to be any consistency or anything. It just says not in there, so it's not in the block.
That's a pretty strong insight. Yeah. That's.
I mean, it's great that Bloom filters provide like certainty on non-inclusion, which is exactly what we're looking for here. So yeah,
this is very insightful. This is like very relevant in terms of like current thinking when it comes to Bloom filters that I hadn't properly considered. So this also means that the original question would be that efficient Bloom filters that are space efficient plus low computation as in terms of making a proof, because essentially, like I was saying earlier, there's the current research and the current presumptions on Bloom filters is optimizations on size and willingness of making computational trade-offs. And we're not able to make some of those trade-offs. So things like Golem-coded sets might become too expensive theoretically.
Right. So yes, you need cheap verification, because every time someone does a withdrawal or every time someone has a challenge, they're going to have to prove on the main chain that their transactions included in that Bloom filter.
Which is not too crazy, because like the optimization of the more optimal structures are like what, 30 or 50%, somewhere in that range, somewhere between like 1/4 and 50%. I don't remember what it was. It was like 1 over something. So we're not talking about like, oh great, you optimize it of like, a 10x increase. We're talking about like, potentially, if it's less than 1 order of magnitude, it's like, whatever, especially if it's less than 2x. Then we can run more naive constructions. But it's still an interesting question, because if we can save, let's say 10 or 10% even, it's like, why not?
Yeah, and where I think the big benefit comes from is what David was talking about, that this is like some data you can keep that isn't that large, that is redundant, like proves a lot about a lot of different things. So if you're verifying like, all sorts of different coins that are all over, like you can't just keep like a section of the Merkle root. You want sort of this some shared data that sort of lets you compress a lot of different proofs. So yeah, so if you only like have one coin, probably easiest just to like look at your own own sort of coin history there, maybe. But although actually, the Bloom filter probably won't be that large. But yeah.
We can make it super tiny by using buckets.
Cool. Yeah.
But it just, as long as it's not like a 10-party multisig, then you have a headache.
It said you have a Merkle tree of Bloom filters here?
No. Basically, what you do is you pre-process it. so that, you know, if the a hash of the output starts with 1, it goes to bucket 1. If it hash 2, go to bucket 2.
Right.
And then on the client side wallet software, you only produce addresses starting with 1.
Right, but what
you grind it.
Right.
Only addresses that start with 1.
But the buckets are like there's one Bloom filter per bucket.
Yeah, that's the presumption that the
Bloom
filter only includes outputs that start with 1 in terms of that.
Right. So there's like 64 Bloom filters.
Yeah. But Bloom filters are efficient in that manner.
Right. But then like, do you have like a tree of the Bloom filters, or like how do you?
Yeah, you make a committed tree of the Bloom filters, basically.
Okay.
Actually, you just append them, but yeah, or a committed tree actually is faster. Yeah, sorry.
Like this, I sort of wonder if it's like, I mean, like, you know, then like if you do that into really small buckets, that's just like a Merkle tree, right? Or something like that.
Yeah. But basically, you're not doing it too tiny. You're doing something like if it's not that high activity, you do 8 buckets or something like that.
Right. Cool.
And then you can make more buckets later on, you know, if you wanted to, and then like at that point, you just watch, you know, if you go from 8 to 64, you watch 1/8 of the bucket, and it continues operating.
Right. Yeah, I do think I mentioned this. Sorry. So that's me. Something I mentioned earlier, which is the adversarial problem of like someone can generate collisions for your ID, so that it'll just sort of make your, like, maybe it'll like review and make your proofs inefficient or something like that. I'm not sure how big a concern that is, but yeah, I think we'd at least I think there might be Bloom filter constructions that solve that, but yeah, we'd have to sort of figure out, just like, is there some way for someone to produce like a really just sort of like degenerate Bloom filters that's like really hard to validate every coin, and that is currently in the set or something like that.
Oh yeah, so the bucket thing potentially breaks if you do that. If you didn't have buckets, you could have some nonce or something like that you change every block theoretically.
Right, maybe that's yeah, but then you can grind ahead on like a long number of nonces.
Oh, the presumption is you don't know until later on or something like that.
Okay.
You base it on the previous blocks.
Sure.
Or the previous.
Yeah,
you know,
I mean, right. There's grinding problems no matter what you do. So
but then you ask just ask the user to keep their addresses private, like relatively private, so that like, I want to give you, but I don't know what your addresses are.
Well, you know what the coin is, because the coin ID is determined at the time you deposit it, and that's what gets Bloom filtered. Yeah. So you necessarily know the entire set. Like everyone knows the set it's committed to in the main chain.
So if you know who deposited the coin, well,
just not that you know who
you can attack a specific coin.
Yeah, but what you want to do is attack a person, not really.
Well, I see. Well, maybe you want to attack every coin, and what you do is you like.
Okay, that's
ID, or like one ID that false positives like all these coins. I don't know. So like that there's like you could sort of imagine someone putting a coin that like causes false positives on like a bunch. Well, you can't do a false negative, so I don't know. Yeah. Wait, so it causes false positives. You do a coin that causes false positives on like every other coin in the set. So like now suddenly it's sort of useless, and you just attack with that every block, and now like you've made the Bloom filter useless. So if there's sort of a way, I think, yeah, you can add
the block creator. I guess the block creator can include a nonce, and they hash it off that nonce, and then
but then that you lose some efficiency there. I think you have to like recompute stuff all the time. I don't know. Yeah. So anyway, these are all engineering trade-offs, which is sort of a way of saying like I'm not very good at that.
A lot of efficiency actually by doing that. Never mind. Anyway.
Yeah.
Well, it still could be worth it.
Yeah, I don't know, but yes, this sounds like an implementer problem. So I've already moved on.
This isn't the implementers call or anything.
Yeah. Right?
Whoops.
Should we end on that note? Oh man, this call was really fun though. Like I felt like we went to a lot of interesting topics. I feel like it's generalizable. That's what I enjoyed about this call. It's like very helpful for like everybody here, but also like it's probably useful for a lot of things.
Oh yeah. This will be recorded in the history books.
We really enjoyed David's thoughts when it comes to movable terrorism and Carl's overview. What's going on in Ethereum.
Yeah, so see you all at EdCon. And audience, hope anyone who's coming, say hi.
Awesome.
Sounds good.
Thank you for watching. And
thank you.
We'll talking to everyone.
All right. Bye.
All right. Bye-bye.
Bye.